Hello, everyone. Welcome to Coffee with Caleffi. My name is Max Rohr. I'm going to be doing the intro slides today. We've got a great topic. I was actually looking back through some of the history of Coffee with Caleffi for the last 2 years, and this DHW balancing just keeps being a really big topic for us. It just attendance-wise, these are the ones that we're getting really big registration numbers for. So today we're going to go into a little bit more detail with thermal balancing, which is the technology that we're seeing the most growth in this category for DHW specific systems. If you're looking for hydronics information, last month's webinar was a good look at balancing for that heating and cooling side of the industry. Today we're going to be talking about plumbing. So I have Cody, Mack, and Kevin Freidt today. I'm going to go through some interesting intro slides, and then I'll turn it over to Cody and Kevin to take over for the content. So we'll go ahead and get started. What do you do if you're having problems with the audio? I changed this slide finally. Close GoToWebinar and reopen it. That's probably the best way to do it. There is an 800 number, and it's probably not worth your time. That usually fixes it. If you want a copy of the presentation, hit yes in the post-webinar survey, and then I'll put this up on YouTube later today if you have to leave early or you want to send it to somebody else in your office. We will put together a certificate of attendance and we can send that around. Depends on the jurisdiction if they accept that, but we can send a PDF that's going to look like that. That'll have 1 PDH on it and some of the action items. Hydronics 34 should be hitting your mailbox this week. I've seen some pictures that these are arriving out in the field. So we also have this as a digital version, but if you signed up for a hard copy, you should be receiving that this week in the US and Canada. This is where you can go to see all of the archived digital versions, hydronics.caleffi.com, including 34, and that will have some additional resources, videos, and things like that that we can link to there and keep adding things. Next month, John Siegenthaler is going to be here to cover a topic that we always get a lot of follow-up questions about that are really detailed: hydronic cooling. How small is too small? Sometimes hydronic cooling in a 3-bedroom house doesn't make a lot of sense for a few different reasons, but how small could you go reasonably to still get the benefits from something like an air to water heat pump that will give you chilled water to use? So we'll go into more of the details of how small is reasonable next month with John Siegenthaler. And then today, we are going to have Cody Mack, he's our National Training Manager, and Kevin Freidt, our Director of Product Management and Technical Services, take over and go through the presentation. So take it away, Cody and Kevin.
Thanks, Max. Thanks, Kevin. So Kevin's going to be driving here, and I'm going to be doing the first few. And so what we're going to do first is we're going to just talk about what we're going to talk about today. So we're going to get into why we recirculate. We're going to talk about why we balance domestic hot water recirculation systems. Might be a little bit on the basic side, but we want to start there first before we dive into the deeper stuff. From there, we're going to talk about the different types of balancing valves for domestic hot water systems, and then we're going to talk about sizing and selecting of those different types of balancing valves. And then we'll get into some of the reasons why thermostatic are getting more popular throughout the country, as well as talk about some of the case studies that we've done in the past, which I think will be really beneficial to kind of understand how these apply in different types of applications. So before we get into that, one of my favorite things that we offer at Caleffi, I think it's our best product, and we don't even charge for it. So definitely take advantage of it. This is our hydronics technical journals. And if you're unfamiliar with these, we offer them in paper copies. You can download them as PDFs. We also have digital versions on our website as well that Max already mentioned. What we're talking about today, though, is most closely related back to issues 21 and 22. So definitely check those out. Great resource for domestic hot water as well as recirculation systems in there too. So from there, we're going to look at basic, simplistic distribution systems and recirculation systems here to start with. When we talk about this, we're talking about heating the cold water that's coming in from your municipality or your well. We're heating up either in a storage tank, a tankless water heater, could be a hybrid heat pump system or some kind of, whatever your domestic hot water production of choice is. Okay, you've got that, and then you've got it feeding out to your fixtures. Now, the problem is with these types of scenarios here on that picture on the left-hand side, the fact is that you're typically going to have anywhere from 50 to hundreds of feet of piping between your domestic hot water production and that last fixture. And so when we look at this, obviously you're talking about opening up a faucet and waiting for long periods of time to get hot water to those fixtures. And so, what are we doing? We're bringing into the mix recirculation. The idea that we're basically creating a closed loop that's bringing back that water from the furthest points in the building and then reheating it through that domestic hot water production, which could be gas, it could be even a swing tank. It would be a little bit different scenario here, but all different ways here to keep that water warm, and we'll talk about why we do that as well. Now, I will say in this very simple diagrams that we've got here, we are not incorporating a mixing valve, and I will say that when you bring a mixing valve into the scenario here, your piping will change a little bit. I've done a couple of these webinars in the past about optimizing mixing valves in domestic hot water systems, so definitely check those out. They're on YouTube already. There's some nice tips and tricks on how to pipe up those mixing valves and make sure that they work properly for you. So from there, we're going to jump into kind of the why we recirculate. And this is one of my favorite graphics here that I use in a lot of presentations when we talk about water conservation in general. And it might look a little bit congested here, in the graphic, but the fact is that it's telling us the projected population growth by 2030 and also the average daily usage for domestic water. And what I find so interesting about this is that you look at the Southwest in general and you see a huge uptick in population growth or projected population growth, but you've also got these areas that are so susceptible to drought, right? So when we talk about conserving water in general, obviously low flow fixtures are great and everything else, but if you can't get hot water, a lot of these people are just turning on faucets and letting them run until the water comes out, and that could be gallons and gallons of water going right down the drain. And so obviously by having hot water right at the tap very quickly, it's going to reduce that wasted water going right down the drain, and it's going to keep that hot water right near the fixture. And it's, again, a great way of conserving water in those areas where you're already going to be more drought stricken for sure. And I'm not quite sure what happened there. And I know, Kevin, you're switching the slide there, but that's all right. I don't know how on earth the state of Nevada uses so much water. They claim that it was 300 plus gallons per day per person. But that's pretty wild. So I joked that somebody must take, really long showers or have that forever dripping faucet. But we talked about it might be irrigation too and things like that. But the fact is there's a lot of water usage out there given how much water they don't have. So, all right. So another reason why we recirculate beyond conserving water is to basically appease the masses, right? We're all used to Amazon delivering the next day. We click on a button on Netflix and we're watching a movie right now. My kids don't even know what commercials are anymore. They have absolutely no patience whatsoever. So the fact is that we want hot water right away. We don't want to sit there and wait. And a lot of times when we start looking at code requirements for the different types of buildings and the different areas that these buildings are in, it is going to be dependent on one of two things. It's either the amount of time it takes to get hot water to the fixture or how much volume of water is in the piping from the recirculated line. And both of these they go hand in hand together, because obviously if there's more volume, it's going to take more time. But the fact is that even in an example like this, if you have 25 feet of half-inch copper, it's going to take over a minute to get hot water to that fixture from that recirculated line if you've got a 25-foot runout, right? And so there again, depending on your area, they could be more restrictive, less restrictive. Some will say, only a certain volume of water, or it can be only a certain length from the recirculated line to that fixture. From there, though, we're finding more and more of these places are actually going to smaller piping. Okay, so instead of your basic half-inch lines to go feed a sink or a touch-free faucet that might be running less than a half a gallon per minute, maybe 3/8 is an option for you as well. So you can reduce the volume of water, reduce the time it takes, and so therefore you don't have to necessarily get as close to the fixture with your recirculated line. So definitely keep that in mind depending on your area for sure. All right, so some things that we need to consider when we're talking about domestic hot water recirculation is we need to try and get the recirc as close to the fixtures as possible. So we talk about runouts, we talk about dead legs. Dead legs should be eliminated from these types of systems, right? A dead leg is a section of pipe that contains water but does not have any flow through it whatsoever. So if you're putting in a T, you're running a section of pipe and capping it off because they're going to put an addition onto this building at some point in the future. That should not be done. That dead leg is going to act just like a petri dish, and it's not a good thing. But when we talk about runouts are those lines from your recirculated risers or branches or trunks that are going to go to that fixture, but we need to keep those as short as possible. One, so we can get hot water out of the fixture as quickly as possible. But two, if you do have areas that are not occupied for long periods of time, you could have basically, in essence, a dead leg. And same thing holds true if you're doing a remodel of a building. You need to take that run out back to the recirculated line if that fixture is being removed. Say you're moving a bathroom group or you're doing whatever the case may be. You don't want to just necessarily cap it off in the wall and leave literally a 10-foot dead leg or a 20-foot dead leg. That's something that we want to avoid if at all possible. The next thing, and it is an issue that we deal with very regularly on our side. We don't sell circulators, but we obviously interact with them with all of our products in many cases. Don't oversize the circulator, okay? When you talk about velocities and flow rates and things like that, most cases you're talking typical recommendations of less than 8 feet per second for cold water for velocities and less than 5 feet per second for hot water. And that's up to 140 degrees. Typically past 140, your recommended velocities are going to be down in that 3 feet per second range. But these recommended velocities are going to be on the distribution side. We're talking more on the copper side of things too. But what about dedicated recirculation lines? What about those lines that you don't necessarily have flow for distribution on or for consumption? You're just having flow through those dedicated recirc lines to bring it back to the domestic hot water production to heat it back up again, okay? Now, if you have dedicated recirculation lines and you're running recirc continuously, the Copper Development Association, just as a quick example, recommends no more than 2 to 3 feet per second, okay? And when you get into a lot of your PEX manufacturers, pretty much everyone that I've ever seen will have something in their literature about keeping the velocities down below about 2 feet per second, right? So half-inch PEX, for example, would be about a half gallon per minute. I think 3/4 is a little over 1 gallon per minute. And so it's really not uncommon to see those lines get sized at half-inch, but then they're running 3/4 of a gallon per minute or 1 gallon per minute. And even on copper, you find a lot of these places are running into pinholing copper and replacing copper sections and things like that. That's something that we want to avoid. So we want to avoid the erosion. We want to avoid the noise, and make sure that those lines are sized appropriately for the velocities. And then last but not least, we always recommend considering a variable speed circulator. Now, if you have static manual balancing valves, which we'll talk about those in a little bit, it's still going to be a little bit easier to set those valves with a circulator they can set a constant differential pressure for. But especially if you're looking into dynamic balancing valves, things that are going to change based on temperature or flow or anything like that, a circulator that is capable of variable speeds or capable of constant pressure or proportional pressure is going to be a circulator that can save you quite a bit of money, as far as energy costs are concerned, for the life of a building for sure, and keep your velocities down as well, like we mentioned before. So another one that we want to touch on is aquastats and timers. Now, I know many of you out there that are designing these buildings have to follow energy conservation codes, right? And so a lot of times they're talking about either demand-based recirculation, or they're requiring some kind of an aquastat or timer. Sometimes they'll even say you could do heat trace tape or something to that effect, to keep this stuff up to temperature. The downside to this is that you're going to have this potential for stagnation, right? So anytime you shut that circulator off on your domestic hot water system or your recirculation system, you're going to have this potential for stagnant water. Now, stagnant water is going to be a perfect breeding ground for bacteria like Legionella, right? So that's one of those things that we want to try to avoid. Now, as an industry, obviously we're trying to conserve energy and conserve water and things like that. But the fact is that anytime you shut that circulator off, you're going to run into more and more issues, right? And so you know, a lot of times we're talking about conservation of energy, and we're talking about how shutting that circulator off can save you a ton of money, you know, and really, you know, over the life of a building or the life of a circulator, yeah, it could add up to quite a bit. But, you know, just as a quick example, you get some of these smaller circulators, and even the variable speed and high efficiency circulators, you know, you look at a model that's going to use 30 watts, right, when it's running, that's going to come out to, we did the math, and it was like 12 cents a day, or like $45 a year, $44 and some change. Okay, I think there's really, you know, a lot more potential for savings somewhere else in the building, as opposed to, you know, compromising occupant health and safety, right? So we want to do that. Now, obviously, if you do run continuous recirculation, there's definitely potential for more heat loss to ambient or to your building envelope, which is then going to have to be made up by your domestic hot water production. But the fact is that's always going to be there. Really, the only thing that you might change there is if it's on a timer for long periods of time where it's not running, you could save money on that. But if it is on an aquastat, the amount of money that you're going to save on energy for, you know, reheating that water is going to be pretty minimal, going from an aquastat versus continuous recirculation. Now, the one thing that we didn't mention on this particular slide is if there is a mixing valve involved, okay, and we get into this a lot, happens all the time, right? And so you have a mixing valve involved. Every mixing valve under the sun has a minimum flow requirement, okay? And that minimum flow requirement must be met by either the demand from the fixtures or with the recirculation. So if you have a mixing valve that has a minimum flow requirement of 4 gallons per minute or 6 gallons per minute, you can make that up with the recirc running all the time, and then you literally don't have a minimum flow requirement for demand at that point. However, if you have an aquastat on there shutting off your circulator, now all of a sudden you're going to run into issues where that mixing valve might hunt, because maybe the flow from your fixtures or the demand is only 1 or 2 gallons per minute. It's not meeting that minimum flow, and so that mixing valve is going to bounce all over the place and even look like a bad mixing valve in those cases, when in all reality it just needs more flow to operate at a stable temperature. So, all right, so we talked about why we recirculate, but now we're going to talk a little bit about why we balance in general, okay? And there was actually a good comment in the questions pane about reverse return piping, right? So, you know, when we talk about balancing in general, when we talk about domestic hot water recirculation, we talk about the fact that water wants to take the path of least resistance, okay? It wants to find the fastest, easiest path after it leaves the outlet side of that circulator to get back to the suction side of the circulator, right? Now, if you had reverse return piping, okay, that would solve a lot of this stuff. But the problem is that you're talking about buildings that are set up exactly the same way across all the risers and everything like that. And that would be probably pretty great, you know, but if you've got buildings that vary in height or length or anything like that, you know, as far as how these recirc runs are going, you know, reverse return might not be your best choice there. So what happens here is that, you know, the closer circuits or the circuits with the least amount of hydraulic resistance are going to get the most flow, and the ones with the most hydraulic resistance are going to get next to no flow. And this is going to lead to people that are, you know, waiting for a long time for hot water. You know, you're going to have wasted water. It usually ends up leading to contractors or building maintenance guys putting in bigger circulators because they think that's going to fix everything. And then they're going to find out about the pinhole copper and premature failed packs and all that other fun stuff that we talked about earlier. Okay. And it's all things that people just don't want to deal with, right? So they want to have hot water as fast as they can, right? So with that in mind, we are balancing these systems so that way you put the proper amount of flow into each riser to make sure you can maintain that temperature to the furthest fixture, you know, and not have too great of a temperature drop by the time it gets there, right? And if you're following anything along the lines of Legionella management, okay, there's the ASHRAE standard 188. All water systems shall be balanced, and a balancing report shall be provided, right? Now, I say that almost laughingly. A lot of specifiers and engineers are requiring balancing reports on their specifications. I'll be curious, do you guys get them? You know, and if you do, are they actual balancing reports, or are they, as some of the contractors refer to it, as pencil whipped? Okay, so, you know, magically they're all plus or minus 10%, just like they need to be, you know, and it only took them a day, you know. So with that in mind, we need to make sure and verify these systems. You know, the fact that you put the balancing valves in there doesn't necessarily mean anything unless they're actually set properly, right? And so with that in mind, when you do have a well-balanced system, you're going to have a short wait time from the fixtures to get hot water, people are going to love that, right? You're not going to have a system that has incredible velocities that's going to lead to erosion and corrosion and things like that in your system, and it's going to be much quieter. You're going to minimize water waste. And one of the case studies we're going to come up with later is a great example of that, okay? You're also going to have reduced potential for Legionella or any type of bacteria growth in those systems. And as we go forward into lower and lower consumption fixtures and things like that, the amount of prevention that we're going to have to deal with for bacteria growth is going to be even greater. And so when we talk about this, though, it's not necessarily just balancing the whole system to a specific flow rate. If you've got parallel branches going off in these systems, each of those branches must be balanced independently, because even if you put a balancing valve on the main return coming back, you've still got multiple branches in parallel that are going to have different hydraulic resistances, right? So it's again going to take the path of least resistance, and you're going to have high flow rates in one area and low flow rates in another area. So from here, though, I'm going to pass things over to Kevin Freidt. He's going to talk about the different types of balancing valves. And before I pass this over to him and he gets his camera on and everything like that, I do just want to mention, we keep an eye on your questions that you guys put in. So if you guys have any questions, don't hesitate to put those in there. If we don't get to the questions during the webinar, we will definitely get back to you in a timely manner. So Kevin, take it away on the different types of balancing valves.
Thanks, Cody. Good job. Let's talk about balancing valves. There are basically three types. Manual is the one that's been around the longest, also called static or pressure dependent. They basically are a restriction in the pipe, and that's an adjustable restriction that will change the flow, but they also depend on the pressure changes. So if there's a set point at a given pressure drop across the valve, if that pressure changes, so does the flow. These are very common. Excuse me, most of them require a balancing tool, and they're pretty labor intensive. The second type are constant flow, or also called dynamic or pressure independent balancing valves, sometimes automatic. So the way these work is that within a given differential pressure range across the valve, they will maintain a constant GPM. So these are not adjustable like a manual valve is. They are fixed. So you order them with a given cartridge, a given 1 GPM, 2 GPM cartridge, and they come that way. If you have to change it, you have to change out the cartridge. That's the second type. The third type is thermostatic. And these are the only modulating type of balancing valves, and we're really going to get into some detail on this type of valve here in a few slides. But they're different. They're not based on pressure drop. They're not based on GPM directly. They're based on temperature. And you can see there's a lot of different manufacturers here, and we're not going to talk about one over the other. They're all very, very similar. There is a fourth type of balancing valve we're not going to cover today, and that's an electronic balancing valve. We're not to that point yet to talk about those. So here we have a poll question. We asked this question quite a while back, and we want to ask the same question again and compare those results. So go ahead, Cody or Max.
So this should be popping up on everybody's screen. Which balancing valve type do you most frequently install or specify, depending on what your role is in the project? Manual, automatic, thermal, or ball valves? And as Kevin mentioned, I've got next to me what we had for results when we asked this question in May of last year. So we're interested to see if this is skewed a little bit. We have some other evidence that I'll kind of talk about as soon as I close this out. But it looks like it is a little bit different from last year as we go through. Also, Cody, to your question about Nevada, I think that all of those Las Vegas fountains and golf courses down there, it's an unbelievable amount of water because it's just so dry out there. And in Utah, where I live, just the amount of water it takes to like support cows, beef cows out in the
and golf courses and everything else. Yeah.
Okay, I'm going to close this poll and then I'll share this. Kevin, I don't know if you can always see this, so I'm going to read these results to you. So we had manual 32%, automatic 29%, thermal 36%, and then ball valves 2%. So I've got good news in two different categories. Ball valves is down 3% last year to 2%, so that's good. And then thermal is actually up from 32% last year to 36% last year. We had kind of a dead heat with manual, automatic, and thermal last year. And that's something that we've noticed in other parts of our day-to-day too, that there is just a trend that people are moving to specify and install thermals in a lot more cases. So I'm gonna close this out and then I'll pass it back over to you, Kevin.
Good, thanks. All right, let's talk about sizing. Here's an example. Let's say you have a specification that has a balancing valve schedule, and just for example, you have a balancing valve requirement for 0.75 GPM, 2 PSI pressure drop, and the designer has put a 2-inch pipe on the plans. So what we'll do is calculate the CV, and there's the formula, GPM divided by the square root of pressure drop. If we plug those numbers in there, we get a 0.53. So now we know what the CV of that balancing valve should be. So for a manual balancing valve, let's find an example. Here's one. This is a specific valve made by Caleffi, and here is the graph in the literature for that valve. So this is a flow characteristics chart. If you look at along the bottom scale there, we have the 0.75 GPM, this blue line here that's going up. And then across the top here, we have the 2 PSI pressure drop. And you can see that if you buy this valve in the 1/2-inch size, if you look down below here, and you set the dial to 1, then the CV will be 0.63. And that's pretty close. So this valve would work for that application. Any comments about that, Cody? It's pretty straightforward, right?
Pretty straightforward on these manual ones, but yeah, I will say it's not necessarily based on pipe size, you know, and I think we'll talk about that a little bit later. That can get people into some trouble. So.
Right, especially with manual balancing valves. If a manual balancing valve has a variable orifice like this one, in other words, when you turn the dial, if it changes the CV, that means it has an adjustable CV or an adjustable orifice. And you can use a few different valve sizes depending on where you set the dial on that type of valve. So there's one example. Let's take that same example, this time same math, same balancing valve schedule, and look at an automatic or a constant flow balancing valve. Now, this one's different because it's based on GPM. So you don't use the CV, which is a little different thinking, right? And in this case, here is an example of an automatic balancing valve, a Y body pattern. And this particular product is available in 1/2, 3/4, and 1-inch, and it has a variety of pipe connections. And since the designer already picked a 1/2-inch pipe, we'll pick the 1/2-inch body. And then you can see over here, this valve comes with different cartridges. So we would purchase that valve with the 0.75 GPM cartridge, and it would fit in there perfectly and control at 0.75 GPM. So it's really simple. And these valves are really popular. They're easy to spec, easy to call out. And when they get installed, it's hard to mess them up, right? Because they're already sized for your design. Whatever you specified on your design is what it's going to be. So that makes it easy. Okay, one more time, this same example. What if we look at a thermostatic valve? Now, thermostatic valves have different CVs. They have a minimum CV, a design CV. Some of them have this bypass CV. That's a little bit different. And then they have a full open CV. So using this example here, this is a particular 1/2-inch valve, and here's the flow characteristic chart. Again, you can see the 0.75 GPM, right? And the 2 PSI pressure drop up here. And you always want to use the design CV. I'm going to talk a little bit more about that in the next slide, but on a thermal balancing valve, look for the design CV. And this one comes really close. So that's 0.52 is the design CV on that one. So it would be a great match for that choice. Now let's look, it's basically the same thing. Let's look at a larger application. So let's say we had a 2.5 GPM design in a 1-inch pipe, and again, a pressure drop at 2 PSI. Similar approach. Let's look at this type of a valve. Again, same thing. This time that is a 1-inch size valve, and here is the information that's in the literature. You can see the 2.5 GPM line and the pressure drop of 2 lines up with dial adjustment number 1.5 on this valve. So that's how you do that in this kind of a product with the flow curves that look like this. So again, a bigger valve. Now let's look at something interesting. That same CV of 1.8, you could get that with a 3/4 inch valve set at position 2 on the dial. Now, the engineer designed a 1-inch pipe, so you might as well buy the 1-inch body, but that could also be done with a 3/4 inch body, right? So maybe it's a little less money, but then you have to add the reducers, right? Cody, you've got to put the bell reducers in there to pipe down. So it would make sense just to put in this 1-inch valve and set it to dial number 1.5. Okay, same thing. Now let's look at the automatic. Okay, same approach, right? We're basing this on GPM, and we don't need to worry about that CV, but this same valve is available in a 1-inch body with a 2.5 GPM cartridge. So again, that would be a good choice. So that's how you choose the automatic valve, is just based on the GPM. All right, one more time. So a thermostatic valve, again, this is a 1-inch valve. So if you look at the flow rate and the pressure drop on the flow characteristics for this one, it lines up really close to the design CV of 1.9. So that would be the right valve for that choice. Any comments, Cody, on sizing? Have you heard any other challenges or issues in all of your travels and education?
Well, I was going to say, when it comes to sizing these valves, obviously we're making sure we have a good authority over the circuits and making sure that these valves can control properly and things like that. I will say with thermal balancing valves, if you are going to continue using fixed speed or single speed circulators, making sure that that circulator is properly sized is probably going to be one of the biggest things that I would suggest, especially in retrofit applications where somebody went bigger and better because somebody in the west wing of the building or whatever was having complaints. You get a circulator that's wildly oversized in these applications with dynamic type balancing valves, is that they're going to end up trying to close off, especially the thermal balancing valves. They're going to try and close off the best as much as they can. They never close off completely, but in all reality, it's going to create a lot of restriction and things like that. And it's not really how they're designed to be applied, or how they're supposed to be applied. So definitely keep an eye on circulator sizing, especially in retrofit applications. If they're remodeling the building or anything like that, confirming that circulator is the right size for the application is great.
Yeah, perfect. Thanks a lot. All right, let's look under the hood, as Bob Rohr would say. Let's look at thermostatic balancing valves. How do they actually work? So if you look in here, this copper colored device here, this item number 2, is a wax sealed element. It's the same kind of element you would find in a thermostatic balancing valve. And all thermostatic balancing valves that I know of have a similar element inside. When it gets hot, it expands, and when it gets cool, it contracts. And you use that movement of the piston in this element to open and close the valve seat. So you can see that here, how that moves up and down to open and close the seat here. Now, they don't fully close. They have to be open a little bit, right, to allow some water flow across that element so the valve knows how to react to the temperature in the system. Graphically, here's what that looks like. Now, this is a graph for that particular brand of valve right there, but basically, when your water temperatures are cold, if the valve is 50, 60, 70, 80 degrees, like if you were just doing startup, right, the valve would be fully open. And as the valve gets warmer, the valve will start to close, and eventually it reaches what's called a minimum CV. So I mentioned that design CV earlier. On this particular valve, that's what this blue line is right here. So that design CV really represents the normal operation maximum opening. Okay, when the system is up to temperature and the valves are all working and they're all dynamically balancing the system and everything's great, as it needs to be, the valve is pretty much going to work right here from about 10 degrees Fahrenheit off of set point to set point. And some other brands have a 5-degree span between their design CV and their minimum, but it's essentially the same kind of thing. So the valve normally operates in this range right here. That's why you use the design CV and not this full open CV. You don't often have that full open CV, only during startup or if the heat source gets drawn down so it's completely cold again. So if you look at it in a system, the branch that needs hot water is going to get the hot water. What does that mean? I just talked about that. Let's say that we had a startup situation and our heat source was just coming online and it was just putting out, cold water, right? All of these valves, the thermal balancing valves, are going to be what? In the full open position, right? They're going to be all wide open. And as water takes the path of least resistance, like Cody said, this valve right here is going to be the first one to get up to temperature. So if you remember that graph we just looked at, this valve is going to start closing down way before all these other ones do. And then when this one closes down, it increases the hydraulic resistance in this first riser, which then makes the water go to the next riser and the next. So that's how these dynamically work. It's basically increasing and decreasing the hydraulic resistance in each of the risers, right? So when they're all up to temperature, say at night when your system is running and there's not any drawdown, and the recirc is all up to temperature, all these valves are going to be sitting at minimum CV. So the head loss in that recirculation loop is at a maximum value, right? Because all of the valves are at minimum CV. So that's why when Cody talked about it earlier, a smart circulator just makes a lot of sense. And we've been talking about using the circulator in constant differential pressure mode, which means that as the hydraulic resistance in the circuit increases, the circulator can slow down and save energy.
I will say too, and to kind of add to that, Kevin, there's a lot of these circulators, the smart circulators out there, especially for recirc applications, that will actually vary their speed based on temperature. And we do get that question quite a bit. If you have balancing valves that are, controlling based on temperature, don't let your circulator try to control based on temperature as well, because they just typically kind of butt heads. Some kind of constant or proportional pressure is going to be ideal for that, as opposed to something that's going to, again, conflict with one another as far as temperature is concerned.
Yep, perfect. So what if you are designing a system and your client wants to talk about thermal disinfection to control Legionella bacteria? That's becoming more and more of a topic of discussion. And there are two factors. When you start talking about thermal disinfection, you need to think of two things: time and temperature. If you look at this graph, you can see the thermometer over here on the left, and then over here on the right are some times. For example, if you expose Legionella bacteria to 140 degrees Fahrenheit, it will die within 32 minutes. Now I need to say here, to qualify this is laboratory data here. When you have a system that has biofilm, or your pipes are not new, then all of this is just a baseline. This is the laboratory numbers and times. But to do that, to do thermal disinfection to control Legionella is used around the world. It has been for over 20 years, and it works. There is only one way to do it, but it's a common practice more in other parts of the world than it is here in North America right now, but we're catching on. So if you remember this graph again, right? So if we are sending hot water down that recirculation pipe, the recirc system, all those valves are going to be at minimum position. Now, that means we have maximum resistance in that hydraulic loop. If we want to do a thermal shock to try and kill that bacteria, we need more flow. We don't want to, with only a little bit of flow, it's going to take a long time really to kill the bacteria. We want to have a balancing valve that can open up, get more GPM going through that loop, and shock and kill that bacteria. So a basic balancing valve that only does the balancing with that single cartridge is not going to work for us. Here's a basic balancing valve. We saw this earlier. So it just has one cartridge that opens and closes. Now, some valves have another feature, a second thermal feature built into the body, and which allows more GPM when you go into a thermal disinfection cycle, and that's what we're going to talk about now. This particular one here that you see actually has another type of body that has a second cavity right here, and with this one you can take the cap off if you order it like this without the balancing cartridge, and your client says, well, yeah, in a couple of years we might want to start doing thermal disinfection. You can install this balancing valve, come back later, pull the cap out, and put in this other cartridge or this third cartridge, and that's what we'll talk about now. Those will allow us to get that increased GPM we talked about to do the efficient thermal disinfection. So if we put that thermal cartridge in this second area within the valve, what this one does, and some of them operate a little bit differently, right? This one actually opens a little bypass passage right here to allow more flow in parallel to the minimum flow. So we have the minimum flow going through this cartridge because it's at or above temperature. And when this one pops open, it opens this other flow path. And what it looks like over here on this graph, these lines here are the normal balancing lines, and adding the second cartridge brings us over here. So do you see how this pink line at 135, it's a quick opening cartridge and it pops up to what's called the CV, disinfection CV. So it will pop open, and then at 150, it will then begin to close down towards minimum to do balancing even while you're doing the thermal disinfection. So this is an integral second thermal cartridge that does this in what's called a bypass way. Anything else to say about that, Cody? Does that cover it?
No, I think you're hitting the nail on the head. Okay. You know, the fact is that, yeah, when you're doing that disinfection cycle, which we're seeing, like you said, more and more of these applications, especially in healthcare and nursing homes and things like that, where people already have compromised immune systems. We're going to see more and more of this, and you know, the idea of minimizing runouts and you know, getting those systems hot once a day is definitely going to be beneficial, and these are a great way to help you out with that.
Yeah, and we do have a whole different training session specifically on Legionella. We're not going to get too deep here. We're just talking about the valves themselves in this webinar. A second option with this brand is to put actually a little zone valve actuator on this second part of the balancing valve. And this is the black line here, this black line. So what you can do is you can actually energize that little zone valve head. It's a 24 volt, normally closed actuator, and pop open that cartridge to do the bypass to increase your GPM. Now what that looks like is this. So what you can do is you can use a building automation system to close a set of contacts and activate this zone valve head, which will pop open the bypass for doing zoning. So you can actually wire that to the BAS and energize it when you want to do thermal disinfection. And on this particular valve, it's another kind of a cool feature. You can get an analog input temperature sensor for your BAS and put it right in here, this little sliding dry well where the temperature gauge is. So now you have an analog input looking at the temperatures for each of your risers when you are doing the zoning control for thermal disinfection.
Hey, Kevin, can you go back one slide to the model with the thermal disinfection bypass, or the thermostatic bypass?
This one?
That one right there, perfect. So there was a great question here about how do these valves know when the system is in a thermal disinfection cycle? Like how do they know when to actually open that bypass? And I think you kind of talked about how that first cartridge closes off when the temperature gets hot, but what happens in that second cartridge, that bypass cartridge?
Yeah, this cartridge right here is this part of the line right here. So it activates at 135, it's fully open at 140, and at 150, then it starts to balance again. So that second cartridge is right here.
Yeah, so that second cartridge is kind of an inverse of the first cartridge, where once it gets hot, it actually opens up as opposed to closing down again. So that's a fully mechanical means of doing that versus the the controls method with an actuator, where you can just open it up, that kind of thing.
Right. So all you have to do is send 145, 150 degree water down the pipe, and this will happen. This second sensor will pop open. Now you can, on this valve too, you can still put an analog sensor in here if you want to read at your building automation system or your building management system. If you want to read all your riser temperatures, that's little dry well still available. But yeah, so that's self-contained. It doesn't require any power, and during normal operation, it just sits there closed.
Yep. So when you get back to your other slide here, there was a couple of good questions about that kind of refer back to water quality, right? And so one of them was, do we recommend strainers upstream of these types of any of these balancing valves? And I will tell you, it's never a bad idea to try and keep this stuff out of balance, anything that dirt and debris and things like that out of the balancing valves to keep them operating and functioning properly. The other question that we had was about thermal balancing valves being stuck or scaled up due to, hardness, magnesium, calcium, so on and so forth, right? Now, the one thing that's great about our valves is that if you do have isolation on either side, which I would always recommend that as well, you can pull the cartridges out of there and descale them or replace them if necessary. But really how often you need to do that is going to be very dependent on the water quality in your area and the water quality in your building, how you're treating the water. Obviously, if you got really hard water, softening that water or treating that water is not only going to help your balancing valves, but it's going to help everything else in the building too, fixtures, bathtubs, all that other fun stuff from getting all scaled up and nasty. So definitely something to consider there.
Yeah, absolutely. And remember, any brand, it doesn't, the water doesn't care what brand valve you have in there, right? It's going to be the same thing. So again, getting back to this option zoning by using a building automation system, we looked at this slide already. So what that might look like, just to sort of bring it back to a system point of view, you could have a number of risers that you call zone 1, for example. And then you could energize those actuators for that zone maybe on Monday night, and then do zone 2 on Tuesday night or something like that, or alternate them. And what that does for you is it means that your central plant, your water production plant, doesn't have to produce enough water and enough volume to do the whole building all in one shot, right? So you can break out. That's the real advantage to having an electronic bypass here, is you can zone it, and your system doesn't have to be as big to provide that high temperature hot water for a long period of time.
And before you switch this slide, Kevin, I think there was another good comment in here too about when do you do thermal disinfection, and not only that, how do you prevent scalding of people during that disinfection? So when do you do it, and how do you protect people while you're doing it?
When you do it is based on testing. So what you want to do is, if you have a client that is interested, or anyone, get a good test kit. Get a Legionella test kit and just sample your water. If there's any indication of Legionella bacteria, then you can start easy. You could say, okay, let's try it every third night. Let's do a thermal disinfection. But basically, it's test and then run it, and test and run it, and you'll be able to tell if the bacteria colonies are increasing or decreasing based on your testing. So get a good test kit, and then you can set up a maintenance program to do this. And then, go ahead. You mentioned anti-scald. You have to have anti-scald protection at every single fixture, any mop sink, any shower, any tub, anything. If you have scald protection, if you have ASSE 1016 or ASSE 1070 scald protection valves everywhere where there's a point of use, you can do this safely. it's okay to send 150, 160 degree water down around your recirculating loop if you have anti-scald everywhere, even in the middle of the night. You know, if someone takes a shower, they'll be protected by that anti-scald valve. So a lot of people get really nervous when you start talking about 150 degree water, but the way around it is just to make sure you have anti-scald.
Yep. And even to the point of too, you know, obviously when you do thermal disinfection, it is going to be based on, you know, the colony forming units of Legionella in your system. But, you know, even what time of day, and you mentioned it before, like typically kind of the middle of the night is usually a good time to do that, where there's little to no demand, and you can take advantage of that period in time. But you, like you said, Kevin, you still got to protect those occupants if somebody's in the middle of the night taking a shower or washing their hands or whatever the case may be.
Exactly.
You can't have 150 coming out of faucets. So.
Yep. So that we can get into this. I mean, zoning, you can get really, you know, complicated here, but this is just a basic conceptual drawing of how you could do that if you have a BAS running things. Now, Cody mentioned earlier that we do answer your questions. We had a pre-submitted question. It looks like we have enough time to cover this question. I thought it was a pretty interesting one. The question was, how does a thermostatic balancing valve compare to a flow splitter? So I contacted someone we know in that industry and got permission to talk about it. And just briefly, now I'm not an expert, but I can tell you a little bit about what these are. If you look at that schematic there, it's a little device that creates a pressure drop, and it causes a water change in the loop pipework when there's a flow in the branch. So even if there's no use of water in the loop itself, it still has a little bit of trickle flow because of that little venturi inside the splitter, and it creates a small pressure difference. And these are pretty cool. You have to design your system around them, right? The piping all has to be designed around using flow splitters, and that is done, and that can be done. They're nice in that they can be put in the hot and the cold water piping. So again, that's a nice thing to know about these. But you still need balancing. These don't balance. They're not balancing devices. They are you know, increased water flow devices. So even if you have a schematic diagram like this, you still have risers, right? You still have those secondary circuits, and they still have to be balanced. So they go together, right? They can work together. Anything before we bring Max back online? I think the next slides are about installations and case studies.
I do have one thing, and we've had a lot of great questions. And like I said before, if we can't get to them, we'll definitely get to you in a timely manner. One thing that comes up quite often in remodel type jobs or additions to existing buildings is the idea of kind of mixing and matching balancing valves with existing balancing valves, right? So say you've got an old building here that had a fixed speed circulator and static manual balancing valves, and then they put on this addition, and it's going to tie in with the existing domestic hot water production and recirc system, and then they want to put thermal balancing valves over here. What are your thoughts on that, Kevin?
Well, the thermal balancing valves will do what they do, right?
Right.
They will, if they're not up to temperature, they'll open. If they're up to temperature, they'll go down to minimum. They will work with anything else. They just do what they do. So
right.
I would think that would be an improvement if you had a zone that was starved all the time for hot water, and you put in a thermal balancing valve and it would be open, then it would let more water get into that starved circuit.
The one thing that I'm always cautious of, though, especially when you're mixing and matching different types, is I usually recommend sticking, you know, like if you've got an existing building, sticking with the same type of valve. It doesn't necessarily have to be the same brand or anything like that, but if you've got existing static manual balancing valves, you know, going with that in the addition. The reason being is that if you have a dynamic valve like a thermal balancing valve, and you've got fixed speed circulators and manual static balancing valves, as these balancing valves over here, the thermal balancing valves open and close, it's going to change the dynamics in the rest of the system, which could increase or decrease flow to those existing circuits. And there's really, in those scenarios, there's no way to actually balance out those manual balancing valves properly when you've got a side over here that's just kind of doing whatever it needs to do, and it's going to do a great job on the thermal side, but then the existing side is going to be like, hey, I'm either starving or I've got too much. And so you know, just from my perspective, when I've run into it before, I would always recommend kind of sticking with the you know, whatever's there, or it kind of an all or nothing kind of thing. You know, if they want to go thermal, replace all of them, go to thermal at that point. Or if not, you know, stick with the same type of balancing valve, because it's just going to make your life a lot easier, and the building maintenance guys are going to be a lot happier, unbeknownst to them, that you that you did it like that. So
this is a good example here. You were on
right.
this job, weren't you, Cody?
Yeah. So this was actually a really cool project, and we actually did a case study webinar around this a number of years ago with a gentleman by the name of Mark Atherton. Very smart man. He invited us out to this job site. This was it was an 8-story building, and it was actually multifamily, and they actually were complaining left and right to anybody that would listen about how they did not have domestic hot water. Now, there were 2 problems in this building. One is that they were not balanced properly on the recirc side of things, but the other problem was they had actually a lot of cross connections in the building, which is we've been running into tons of these issues with cross connections that look like a bad mixing valve or look like improperly balanced recirculation systems. And so in this particular case, the tenants of this building finally got around to calling the Denver Health Department. And at that point, you know, the health department said, if you can't get them hot water, you know, you need to put them up in a hotel until you do. And, you know, some of these tenants were turning on their faucets and their shower valves, their bath fillers, and they were turning them on for 20 minutes, 30 minutes, 40 minutes, they would never get hot water. And it was because those cross connections at the single handle faucets that, you know, the failed cartridges and things like that, they would act like a mixing valve downstream of the actual mixing valve that was supposed to be doing the mixing. And so they would literally never get hot water. And what was cool about this is that this part wasn't cool, but the original job was 28 risers, and they're all balanced with ball valves. And what do you know? All the balancing valves are wide open, right? And so they went through, they fixed the cross connections in this building. That took a long time to do. Then they replaced all 28 of those balancing valves with thermal balancing valves. And I think what was super cool about this, you know, you talk about energy conservation and water conservation. The number that was thrown out for this from one billing cycle to the next is they saved, I think it was like 30 to 40% on their water bill from one to the next. I mean, the work that they did in this building probably would have paid for itself if they would have done it years sooner, right? Versus waiting until they were threatened by the health department, kind of thing. So it's definitely something that you need to consider, not only for the cost of water, but for the conservation of water as well. So
here's a really cool job. You want to talk about that one?
Yeah, sure. So this was a building. This was actually a high-end residential building, right? And in this particular building, they were home running their recirc back to the mechanical room. Not typically something you're going to do in a lot of your commercial buildings, right? But they were home running their recirc back, and in this particular case, they ended up putting in a bunch of our thermal balancing valves in here in order to complement that nice variable speed circulator that was right down below there. And this is what allowed them to get proper hot water and get hot water to those furthest fixtures, all those bathroom groups that had the home runs there. And it was a really cool job, really nice house, you know, and nice. I think they did a nice job. So
good. Yeah, by the way, these case studies are available on our websites if anybody wants to get them.
For sure.
So just let you know.
Yep. And this was actually one case study where it was a high school in the New England area, and they actually not only were using thermal balancing valves, but you can see there they were actually using the actuators on the bypass cartridge. So they were doing thermal disinfection in this particular building. They were doing it once a week. I think it was on Saturdays, if I remember correctly, and getting it all set up and everything like that between the thermal balancing valves as well as an electronic mixing valve to go along with it, which was a great question. We actually had a comment from in the questions box about how you adjust the temperature to do this thermal disinfection. Now, obviously, if you're on site, you could walk up to the mixing valve and, you know, jockey it around to get the temperature that you need. But there are electronic mixing valves out there that you can program and automate this process with, to where, you know, every night at 2 a.m. or every other day at 2 a.m., it will increase the distribution temperature to whatever you want. They even have a dry contact relay in there to then go back to your mechanical controls to increase the storage temperature, or go back to your building automation system to increase the set point temperature of your storage tanks. There's lots of ways you can go about doing this that is pretty hands off, you know, so it really makes life easier, because, you know, we don't want to add more things to the plate of the building maintenance guy. You know, an automated procedure for this would definitely be beneficial.
Yep. All right. Let's bring it home. This is our technical team. There's me and Cody. We look kind of familiar. The other two guys on the left are also tech support guys. So if you call us, we answer. And we also have that techsupport.us@Caleffi email. Feel free to use that.
For sure.
We are all over social media, probably as much as anyone is, and we love to see your posts. Send us your Instagram pictures of your installations. If you have design questions, give us a contact. We use all of these social media platforms. And I think we have a couple of, well, we're right at 1 o'clock, but if anybody wants to hang around, do we have any other really good questions, Cody, that you want to address before we call it a day?
There were some good ones. One of my favorite ones, there was a question in here about how do these balancing valves work in buildings with different pressure zones. And I would say, if you have a building with multiple pressure zones with pressure reducing valves, you know, say you got a boosted building because you got a really tall building, you got a boost to get to the top, right? And obviously at the bottom of the building, you might have 120 or 150 PSI. You can't send 150 PSI to those fixtures off that riser, right? So you got to use a pressure reducing valve. Well, the problem with that, and it doesn't matter what the type of balancing valve is, static, manual, or automatic, or thermal balancing valves, none of these balancing valves are going to play well if you don't do this right. Okay, so the big thing is that you come off that riser at 150, you knock it down to 75 or whatever, you know, sooner or later at the end of that run, you're going to want that water line to come back and get reheated. Well, you've got a 75 PSI line trying to get back into a 150 PSI riser, and it's just not going to jive at that point. And so we've done a couple of webinars about this in the past, about doing domestic hot water recirc in high-rise buildings, but basically you need to separate those pressure zones. They cannot, you know, intertwine, right? And so a lot of times these are getting separated and reheated by plate heat exchangers or small electric water heaters and such like that. But the general consensus is that it doesn't matter what the type of balancing valve is, unless you separate those pressure zones, even on the recirc side of things, there's no balancing valve that's going to play well in that scenario.
Yeah.
So
If you typed in a question or sent in one earlier and we did not get to it, I'm sorry about that. We do, however, follow up all of your questions with emails. So as long as we have your email and you have your question in there, you'll hear from one of us.
For sure.
So, thank you, Cody. Thank you, Max. We will let everybody go. We appreciate your time. See you next month. Bye.
Bye, guys.